All right, we have a hefty lift today with this topic, implicit differentiation. Like, you probably know what differentiation is, but the implicit part should sound like what? Oh, let's go with this blue. Okay. So implicit differentiation is the way that we take derivatives of implicit functions. So if you don't know what that is, you're going to have a hard time figuring this out, right? So an explicit function is the way that you've been raised in math, right? We have taught you, y equals 4x plus 1. That's explicit, right? Y equals sine of x. That's explicit, right? X cubed plus 2x plus 1. That's an explicit function because it's solved for y, and all the x portions are on the other side all alone. So an implicit function are like these two that you see here. And in fact, calling these functions is a little bit misleading because if you look at the second picture, that ain't a function, right? That does not pass the vertical line test for that portion of the graph, does it? So there's a whole world of functions out there that are written where x and y, right, neither is solved for the other. They're just kind of combined to make an equation. And these are actually the most interesting kind of functions to look at, and probably the things that we use most, to model real world data. Maybe not the one on the right, but, they allow us to work in both x and y to create kind of some movement in the graph, unlike we can when it is y equal to a function of x. So what's weird about this is it's still our job to find, right, like let's say the equation of the tangent line right here on that function, right? It still has a slope right there, and therefore it belongs in our repertoire. So, other things that we're going to learn eventually too is, sometimes to find maximums, right? Like in this particular part, that point is a maximum because the derivative equals 0 there, and that's an interesting point for this function, so on and so forth. So we're going to go ahead and start to look at just some basic ways to take these derivatives. So in the first example, okay, I ain't beating around the bush here. This is a circle, right? You should know that this is the graph of literally the unit circle, right? Because its radius is 1. So if I needed to know tangent lines, at any of these spots, you would need to take the derivative using this process. So here we go. So usually what we do is we rewrite the problem, and then to show that we understand notation and have a high command of this, we write ddx in front of that to show I'm about to take the derivative of this with respect to x. Okay, so the first term is easy, right? The derivative of x squared is 2x. But if we're taking the derivative of y squared with respect to x, it gets a little bit more complicated. So it's luckily, you have all the tools that you need. The derivative of y squared is 2y, right? That's just following the derivative rules because it's a power, right? But then based on the chain rule and this idea that y actually, you could rewrite this function explicitly. In some cases you can, in some cases you can't. This one you could. So what we have to do is we have to multiply by the derivative of y, which we're just going to call dy dx. Okay, that's like the chain rule. Okay, so we don't have anything, to call y prime other than dy dx. So anytime this rule gets set up where you're differentiating and you come to a y variable, you always, always, always are going to have to apply this multiplier. Okay, so now we're going to go ahead and we're going to solve for that dy dx because that's representing the derivative, right? So I'm going to subtract 2x from both sides. I get 2y dy dx equal to negative 2x, just algebra there. And then I'm going to divide everything by 2y. That cancels out. And then I have this statement, the derivative, right, dy dx equals, if I cancel the 2's, negative x over y. So this derivative is implicit as well. It's based off of x and y together, okay? So now, let's see. This is the point, let's look up back on the circle. This is the point 1, 0, right, on this circle. So if I wanted to know the slope right there, right, well, it's that part of the circle, so I'm expecting the slope to be undefined. So if I plug in 1, 0 in the appropriate spots, right, I get -1 on top, 0 on the bottom, and that is an undefined slope there. So it does crank out the derivatives just like other derivative rules, you know, or it does, I should say it does generate slopes just like other derivatives generate slopes in the same way, okay? All right, so example 2 is actually this picture up here, this crazy, wiggly, right, x plus sine y equal to y function. So we're going to do the same thing. We're going to write down the function, and as our first step, notationally, is to show that I'm taking the derivative of that function, right? So now the derivative of x is pretty easy. It's just 1. The derivative of sine y is going to be cosine y, but because it's the wrong variable, I have to multiply, right, by dy dx. Okay, you can think of it like the chain rule. Now, the derivative on the right-hand side, the derivative of y, since it's just a variable by itself, is 1, but we have to multiply by dy dx because it's the wrong variable. Okay? All right, you can hear my dog snoring in the background. All right, so now we're going to solve for dy dx in this one. It gets a little more interesting because we have 2 dy dx's, right, in this example, unlike the last one. So I'm going to group those on the same side and factor them out. So I will probably write nope, not 1 plus. I will probably write 1 equals, okay, 1 dy dx, and then subtract the cosine y to this side. Then I'm going to factor out the dy dx from each of the terms on the right and get left with this. And then I'm going to divide, right, by 1 minus cosine y. So dy dx in this problem is 1 over 1 minus cosine y. Okay, so that means that the slope at any point on that function is dependent on the y value itself, right? Not necessarily what the x is. Okay, let's go on to example 3. This brings in a rough situation. So if we look at example 3, there is something new going on here, and it's the fact that we have x times y, right? Which x is the good variable and y is the bad variable. Y is the one that makes this harder for you. So in order to take this derivative when it comes to it, I'm going to have to use the product rule. Okay? No ifs, ands, or buts about it. So let's start to take this derivative. I'm going to rewrite the original function. I'm going to go ahead and take its derivative, right, using my ddx notation, and then I'm going to take the derivative term by term. So the derivative of x cubed is 3x squared. The derivative of y squared is 2y times dy dx because of that implicit multiplier, right? And now when I take the derivative of 6xy, I have to think of it as 6x times y, like this, and think of the product rule as 6x is my f function and y is my g function. Okay, so I'm going to take the derivative that way. So it's the first function times the derivative of the second, and the derivative of y is just 1, but because it's a y and not an x, I have to put times dy dx, plus the second function, which is y, times the derivative of 6x, which is just 6. All right, so here's what's weird. In this problem, all the calculus is over with, right? The calculus in these problems is 1 line long. It's just the part where you take the derivative. Everything that comes after that is algebra, 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 right? So I'm going to do the same thing as I did before. I'm going to group, I don't know, I kind of did that awkward last time. Usually what we do is we group the dy dx terms, right, this guy and this guy, to the left-hand side. So I'm going to keep the 2y dy dx here. I'm going to subtract the 6x dy dx. And then I'm going to, get this term minus 3x squared, to this side. So that on the right-hand side, I just have these two terms, 6y minus 3x squared. Oh God, what is that? Oh, why does this thing keep doing weird things to me? Okay. 6y minus 3x squared. Now, if you're a kid that has sloppy handwriting, you can't make your y's sloppy and look like x's because you could be in for some bad calculus when you do that. All right, now let's go ahead and factor dy dx out of here. I get 2y minus 6. This side is unchanged, and then I'm going to divide by 2y minus 6. Okay, so my final statement is that dy dx is 6y minus 3x squared all over 2y minus 6. Okay? So again, let's think a little bit about this product rule happened here. So I had to think of that term as 6x being the first function, y being the second function, and then this is where the product rule actually existed in my work. Okay? If we want to annotate this, like if those of you that love step-by-step, okay, first thing we do, right, is we take the derivative. Okay, remember the implicit multipliers. And then the second step, right, all the rest of this is that we're solving for dy dx. And generically, we tend to move dy dx to the left-hand side, and then everything else to the right-hand side. But of course, I didn't do that example 2 because I'm a ding-dong. Okay, example 4 here. Find the equation of the tangent line of x squared plus 4xy equal to 13 minus y. So here is the function, right? And we're trying to find the tangent line at x equals 2. So what I know so far is this. I got to figure out my slope, and I have to figure out my y value. So let's do my y value first, because at least that's just algebra, right? That has nothing to do with calculus. That means plug in 2 for x and solve for y. Okay, so I've got 4 plus 8y equal to 13 minus y. Let's add y to both sides to get 9y, and then let's subtract 4 from both sides to get 9. Oh my God, isn't that convenient? Y equals 1. Glorious. So that is going to go up here in the y spot. And then let's go ahead and take the derivative of this function so we can go ahead and find the slope. Okay, so I'm going to write down x squared plus 4xy equal to 13 minus y. And then I'm going to take its derivative using, big kid notation. The derivative of x squared is 2x. The derivative of 4xy is a product rule. So 4x is my first function and y is my second function. So it's first times the derivative of y, which is just the number 1. That's its coefficient, right? And then the derivative has to be implicit for that because it's the wrong variable. Okay, plus the second, which is just y, times the derivative of 4x, which is just 4. Okay, so all of this is my product rule. And then equal to -1, right, because that's the slope of this one term, is -1, times dy dx, because it's the wrong variable. And then I'm going to solve and get all the dy dx's on this side. So basically I'm going to add, right, dy dx here so that it cancels out. Then I am going to move this term and this term, which don't have any of any dy dx in them. So I'm going to move those to the other side using my opposite. So that's -2x minus 4y, right? Oh, yuck, ugly. Okay, and then I'm going to factor out dy dx, which leaves me with 4x plus 1. I get this. And then I'm going to divide by that bad boy. So my derivative is -2x minus 4y all over 4x plus 1. Now, I have to go back and insert my x value of 2 that was given, right, and my y value of 1 into this problem. Okay, So let's just go all pink here. So this is negative 2 times 2 minus 4 times 1 all over 4 times 2 plus 1. And that is negative 4 minus 4 all over, let's see, 8 plus 1 is a 9er. And that is negative 8/9. So I'm going to put my slope up in here as negative 8/9. And that is my tangent line equation right there. Okay. All right. I'm going to show you one last one here. It has the product rule in it for the first term. As you can see, the x and the y are in the same term. And it also has sine of y, which we did not have up here when we did... Oh, no, we did. We did do sine of y before. So actually, I'm going to bail on you. I'm going to have you guys try to do this one on your own. I'm going to jot down the answer here for you so that you can see if you can get to it on your own. And then if not, we can kind of pick up on that one in class. So dy dx in this one ends up being y squared all over cosine y minus 3 minus, okay, come on, minus 2xy. Okay, so see if you can get to that starting here. Okay, all right, don't forget the product rule here. And all the terms on the right-hand side are going to need dy dx's in them. Don't forget.